Hello and welcome to the New AE Technology Inc. tutorial for the VCC glitching with the ChipWhisperer and AVR target. So I'm going to be doing this in a ChipWhisperer instant again, and it's worth noting, so you might want to look at the Git repo. If you do a Git pull, this always gives you the most up-to-date CD ChipWhisperer. In this directory, this will give you the most up-to-date version of the ChipWhisperer. So I'm already up-to-date. You might see some stuff come across here. And this is important because some of the stuff we'll be using depends on more recent updates to the ChipWhisperer system. Alright, so to begin with, what I'm following along with, by the way, for reference, so if you have the ChipWhisperer documentation, there's this VCC tutorial, A3 VCC glitch attacks. So with power glitching, what happens, how this works, is that we actually have the glitch output of the ChipWhisperer Lite, or if you don't have the ChipWhisperer Lite, if you use an external MOSFET, all it does is it shorts the power rail, and it uses the fact that we have this shunt resistor in the target board that lets us nicely short it in a very precise manner. If you don't have that, you can actually still do these attacks. So another part of the tutorial does them against a Raspberry Pi just off the shelf. You can still perform it, but it takes a little more finagling typically. So this shows, for example, what some of the power traces might look like when we're doing the glitches. So you can see we have the regular power. And when we insert the glitch, it gets shorted down. And this short is done in quite a precise manner because of how the ChipWhisperer Lite works. It has, the bottom trace here is the clock, the top is the power rail, so it shorts it at a very precise instance in time. And you should have already done the previous tutorial, the glitch attacks, because this introduced the Glitch Explorer, which we're just going to jump right into. So the Glitch Explorer is how you adjust parameters of the glitch attacks in order to figure out how they work. And in particular, how wide these glitch pulses need to be and where they occur relative to a clock pulse. Alright, so as a first note, right now the tutorial, and you can check the documentation for an update on this, doesn't have the details for the ATMega attack. This is because the ATMega is a lot more sensitive to parameters of the glitch. So it's easier if you have an external AVR target. So this is the not Arduino board, or if you had the multi-target board, this would work too. So here's the hardware setup. You can see I have the ChipWhisperer Lite that has been broken apart, and I've connected both the glitch and measure cables. Technically, you just need the glitch cable, this top one here. But if you attach the measure one as well, this will let us measure the power consumption and see what the glitch is doing to the power rail. A note on this board, these two SMA connectors just go to the same spot. So if you just had one connector on your board and you wanted to have both, all you need is, a short sort of Y cable here. You don't need a proper 50 ohm match splitter. You in fact don't want that. You want just a direct short splitter off your one output. Alright. As a note, if you don't have the Arduino and you don't have, or if you don't have the ChipWhisperer Lite, if you have the original ChipWhisperer Capture, what it had was it had a separate board that had the little MOSFET on it for shorting. So I won't be using that in this tutorial, but you can go through the documentation here that tells you how to mount that. So again, if you have the ChipWhisperer Lite, either in the case or on the board itself, you do not need that separate board. It's already built in. So in a similar manner to the clock glitching tutorial, we're going to attack the glitch 1 function. So I assume you've already done the clock glitching tutorial again. And if we look at what the glitch 1 function is, it just went into an infinite loop and waited there. So we talk about that a little further, but if we go to this tutorial, we can see the source code somewhere. Where is it? We want the glitch 1 source code. So you can see what it's doing is it goes into this infinite loop here and then just waits. So that's where we want to be. Okay, So, to begin, again, I'm going to be going through the ChipWhisperer Lite. There's a few small changes depending on the hardware you're using, but if you're using a ChipWhisperer Lite with an Arduino, you can sort of directly follow along. So I'm going to open the ChipWhisperer capture, and I'm going to select the ChipWhisperer and open ADC. Actually, before that, I'm going to make sure the ChipWhisperer Lite is connected to my VM here. For the target module, we select the simple serial. And on the scope tab, we want to make sure this is set to ChipWhisperer Lite as the connection. And same thing with the target setting, set it to the ChipWhisperer Lite. So we've set the scope module, the target module, and then configured each of those. We can now use the master connect, and everything should connect up here. Everything goes green after a second, indicating this worked. And if we look down here, in the debug logging, Windows a little off screen on the resize the VM here, you can see that it connected okay. So the next thing we do is we need to set up the clock generator. So we need to generate a 7.37 megahertz clock. So we're going to, right here, we're just going to switch our frequency counter so we can confirm the output. And, by default, it has some other 192 megahertz. So we just set the desired frequency to 7.37. And you can observe here it is generating the correct frequency. It might be a tiny bit off on either the measuring or generation, but that's more than close enough for us. We also want to set the glitch module. So again, we're using the clock gen source. So there'll be some changes later on. It's not the same as the previous tutorial, the rest of these settings, but we do use the clock generator source. The other thing we'll want to do is the target I/O out. We can set to either a glitch module or clock gen, depending on what you want, depending on what hardware you have. So if you are using the ChipWhisperer Capture Rev 2, you set this to glitch module. For the ChipWhisperer Lite, we would set it to clock gen. Before we do that, one thing to change is the output mode of the glitch module. You should make sure it is set to glitch only. So why we do this is this ensures that we are not continuously generating a stream of glitches, which if you have the ChipWhisperer Capture Rev 2 will be turning on the shorting MOSFET, which could damage things. So make sure output mode is set to glitch only. Alright, so now that that's done, I'm going to set the target I/O out to clock gen, again because this is a ChipWhisperer Lite, and that's the clock that the AVR uses. Right, so now things should basically be working. We can connect the serial port, and so this will give us the serial port to monitor the output of the AVR device. So now that we have that, what we have to do is program the appropriate hex file in. And actually, I should have done that earlier. So as before, we're going to go to the ChipWhisperer, hardware, victims, and then we want the firmware directory. Inside this, there's the glitch simple. So this was the same directory we used for the clock glitching, but it's going to be a bit different for the voltage glitching because there's two things to do. Number one, in this while loop, in the glitch simple.c, so if this doesn't open automatically, you can find it again in that directory, glitch simple.c, which is in ChipWhisperer, hardware, victims, firmware, glitch simple. And down in the main loop, there's a bunch of example glitching things you can have. So by default, I think it has glitch infinite, so you want to change that to glitch 1. The other critical thing to change is we have to open the make file. By default, this targets the ATMega device, and we are not actually targeting that. We're targeting one of the AVRs. So you either want to enable the Arduino kit platform or the multi-target platform. Okay, so now that I've modified that, we can just run make in this directory, and it should build successfully, and it says right here, built for platform CW Lite, not Arduino. So that means we've now built the appropriate hex file. So I'll use the AVR programmer built into the ChipWhisperer Lite, and what we'll do is we will point it to that, oops, not software, hardware, point it to that hex file I just built. And you should always check, modified. It was modified 1 minute ago. So that means it's the right hex file. We didn't have a separate directory with it in. If I hit erase program verify, it gives me the verified flash OK. Over here on the capture, what you'll notice is it printed this hello A. So this is the same as if you did the clock glitching tutorial. You will recognize this. If I hit check signature, it resets it and reprints that. And if you have the Arduino board, there's actually a small reset button, push button S2, that you can press and also confirm. It's just resetting the program and rerunning this. There's a warning in the documentation, just as a note. The AVR programmer in ChipWhisperer capture prior to 0.13, so up to 0.12. So there it is. When you use the AVR programmer, the reset logic, it never released the chip from reset. So make sure you update to finish this tutorial, just as a note. Okay, so we have the output mode set to glitch only. Now we have to decide what happens for the glitch. With the ChipWhisperer Lite, you won't have this option with the Capture Rev 2, but with the ChipWhisperer Lite, we also want to enable the low power glitch. And again, before we did that, we made sure that the output mode was glitch only. Otherwise, when you check that, it's going to cause a whole bunch of glitches to go across the wire, which you don't want. And you can confirm that the clock source on this was set to clock gen for the glitch module. The final thing to do here is that, so when we insert the glitches, we want to automatically insert it when we reset the AVR and it goes into that loop. So just go ahead and set it to external trigger single shot. So single shot just means it only inserts one glitch per capture cycle, and you really want to use this so the continuous mode by comparison, what it's meaning is every time there's an external trigger, it inserts a glitch, regardless of if you rearm the capture or not. Why that's dangerous is that when you insert a glitch, it may reset the AVR, which causes another trigger and just causes another glitch, and so you get into an infinite loop and you can't break out of it. So the single shot mode means it inserts a glitch and then disarms the trigger until you hit capture 1 again, or if you're doing a multi-capture, until the next capture cycle. So that's the much safer option. So now it will automatically trigger when there's a trigger glitch when the IO line goes high on the AVR, indicating it's come out of reset and running the program. The other thing we want to do is we want to automatically reset the AVR before every capture. So we do this with one of the Reset AVR auxiliary modules. If it's the ChipWhisperer Lite, it can do either the ATMega or AVR reset. We need to make sure we change this to AVR. And you can hit test reset, and what you should see is, again, in this terminal emulator, you see the startup message. So that means things are working just as expected. Okay, that's good, that's good. Finally, the final little bit of setup is in this target setting commands. We want to delete all of these, this text here. This means that, previously it would send some crap to the device and wait for the output to save to a file. We don't want any of that. So if you hit capture 1, for example, you'll actually see it prints a hello because it's resetting the device and putting the output to the terminal port. So that's the main setup. One of the optional things we could do is we can actually monitor the glitch insertion. So this is this section of the tutorial here. So what we're going to do is we're going to set up the ADC to monitor the power consumption. And this is cool because you can see when it inserts the glitch, it's dropping the power rail way down. So as you expect, you see that in the monitored power of the device. So it's a good way to verify things are working. So this is pretty straightforward. To do this, we'll go through all the scope settings. So the first thing we're going to do is we're going to change the ADC to be clock gen times 4. And you need to reset the ADC DCM, so this means we're now sampling at 29.5 megasamples per second. In the trigger setup, we'll set this to a rising edge trigger. And we'll only capture 1,000 samples. We also will set the gain mode. I'll set it to about 40. You can play with this depending what you want. And with that, you should be able to hit capture 1 and get a working, some sort of waveform. So that's what I have here. All right. And if you play around a bit with so right now it's not really inserting a glitch. It's all enabled, but the glitch width is set to 0. So, if we set that to 49, which is almost the maximum, you can see this massive, change. Holy crap, look at that. So that's when it killed this power rail, and you can see right in the power consumption here. And you can do stuff like we could add an offset. So we can say, hey, let's, wait 100 cycles of the device, and you can see it moves way over there. Or we can reduce the width of this glitch, and we see a much narrower device. We could, repeat it a bunch of times, so we see a whole bunch of glitches inserted in a row. But, that's kind of cool to see, but it's not actually giving us the useful glitch attack itself. So, the next thing we want to do is let's use that glitch explorer to break out of the loop. So, if you remember from before, so this is this section here, it sends 1, 2, 3, 4 after it exits the loop. So you can look at that in the glitch simple here. So there's an infinite loop, and it puts 1, 2, 3, 4 out. So that means it was, it broke out of what should be an infinite loop if we insert the glitch correctly. So to sort of test this, we're going to use the Glitch Explorer. The first step of using the Glitch Explorer is setting the output format here to glitch. So this will reroute the output to the glitch monitor, and it'll no longer go to the terminal when you hit capture 1. Oh, output format, sorry, not go command. So you can now see that it's coming across here. And one slight difference from the clock glitching, it's not as reliable on what the starting phrase is. So we want to mark these as all sort of okay. And the nice thing here is we can use a little bit of Python code to figure out what our success or failure should look like. And so to do this, I've just resized the window here if it suddenly changed on you. There's a Python console, and this is a regular Python console. So I can, for example, see, well, let's use this example string. So I've now set the S variable to the string we want to test. And previously we had seen that you could use the ends with, function here. And we could say, well, if it ends with that, it's okay. So it returns true, meaning that it's going to consider this, a normal response, for example, if we just pop this in here. But that's not going to catch if it resets, it's going to print hello again. And maybe it'll print some crazy characters. And so it's, oops, that's not what I wanted. So it ends with hello. What I want to do is set the test string to something else. So let's pretend it resetted. and we get this. And if I run the ends with, it says, that's a normal response too. So we're going to add a additional thing. We're going to say if it ends with that and the length of S is less than, say, 12 characters. So this allows some garbage at the beginning, but doesn't allow it to reset twice. So you can see now it's saying false. So we're just going to pop that in the normal response. So this means if it sees it ends with the hello and A, and it's short enough to not have reset after the glitch, that's a normal response. For the successful response, we just want to see if 1, 2, 3, 4 is in that string. So with Python, we can just type 1, 2, 3, 4 in S, and in that case it's false because it wasn't a successful glitch. And this will catch the case where it actually prints it and then resets. So we might get that and need to tune it a little more. So that's the configuration we need. The other thing to configure is the scope, or the default glitch settings. So this is under the scope settings glitch module. So we're going to sweep the offset using the glitch explorer, but I'm going to set the glitch width to 49. I'm just going to fix it at a very high number. I know for the AVR that tends to work to make this tutorial a little faster. And I'm going to have a repeat of 10, so it's going to glitch 10 cycles in a row. You can see, on the waveform if you want, it looks quite extreme here. And you can see in this case, it actually didn't even reset the AVR, it appears. So despite this extreme glitch, it's not resetting the device, which seems pretty good. So the final thing to do is let's make the glitch explorer sweep our parameter of interest. So we say we have one parameter to tune. And what is that parameter? We'll configure it right here. So the parameter itself is the glitch offset. And again, the first thing we do is we just adjust it on the GUI. And this prints in the script commands what the script string is to modify that parameter. So we'll pop it in here. We'll give it a nice name so that in the GUI you can see it appears as that nice name. Offset. And we're not sending anything, so you can reduce that. We're going to adjust it. We're going to use it as a floating point number. Again, this you can insert a decimal here if you want. And I'll range from -49 to 49. The starting value I'll put at the beginning range. And for this step, I'll put 0.5. As a note, if you wanted to get every possible, phase offset, you'll notice that when you scroll through this naturally, it's upgrading by this, or it's changing by this 0.39 something percent. That's the intrinsic step size of the hardware. So you could actually put that step as 0.39 if you want, and that would give you every possible phase combination. 0.5, some of them, might overlap, or it's actually going to miss some possible phase combinations, but I know the AVR is not too picky, so I'm going to use that to speed it up. The final thing to do is say how many traces we need to record. We'll set it to 200 because there's, about 100 in here, and then a step size of 0.5. And there's no trace format because we're not recording the power data. And then we just hit capture. It warns you that there's no trace radar, which is totally fine for us. And now we sort of wait. So this part isn't too exciting. So I'll just pause it for a second and we'll come back once it's starting to successfully glitch this thing. So here you can see, actually here is one successful glitch, so for a specific offset. Oops. I'm going to let it keep running so you can just see it scroll by. This offset of -35.4, and that worked great. It didn't reset afterwards either. Oh, there's another one. So we're starting to see a few. And you can see at the bottom it says 2 of these glitches have been successful. You'll note it'll count success as the case where it outputs 1, 2, 3, 4 and then resets. You'll see that sometimes too. But with any luck, you'll find a variety of useful glitch parameters. So let's keep running and see how many else we get. And actually before that, one thing that's interesting here, we're getting some failures. But you'll notice it's printing, it's actually printing like password and denied. It's printing these other strings. And where those came about is those strings were actually in the source code. You know, they're not called at all, but this other glitch 3 module had those strings in it. So it was actually dumping some of these other strings from elsewhere in the device, which is pretty interesting to see. So you can see why glitching does more than just, you know, basic stuff. So here we're starting to get, this is good, we're getting a bunch more success rate. So we see, this is nice because it looks like this must be a much more reliable offset. You know, you can see it sweeping through quite a large range and glitching successfully the whole time. So at this point I could actually just stop it and we could, you know, pop in -7 as the glitch offset. So if I put that in, and we're just going to hit capture 1, and we'll see if that's very reliable or not. And it doesn't seem to be super reliable because even though we're getting a bunch of glitches here, when I test it, it doesn't seem to be working. So you may have to, but a -8 did work. So you might have to go through your range a bit and see. One thing to note is that with the current version of the software, the offset I put in here is sent to the device, but it's not sent back to the Glitch Explorer. The Glitch Explorer generally assumes it's setting the parameters, not you. So when you override it like this, it's putting the wrong offset in the table. But you can see I was able to reliably glitch the simple example. So what you can do next is you can try to reduce the repeat number possibly. So you can see, can I glitch with only 5? So in that case I can't, but you might have to run Glitch Explorer, and you can run it over a shorter range now that you know you have some idea of where the reliable glitches seem to be happening. So it's this smaller area here. Or you could see if there's another reliable area entirely. Once you do that, the tutorial will eventually be updated to include the recreation of the Raspberry Pi attack, which glitches a completely different embedded target, but with the same sort of stuff. So hopefully this tutorial has showed you how you can use the crowbar VCC glitching that's built into the ChipWhisperer Lite, or you can build with a MOSFET externally to glitch a embedded target and bypass some of the security features that target might have. So thanks for checking out tutorials.